Welcome everybody. Stat 243. I think this is lecture 7. We're going to be focusing on chapter 4, specifically binomial distributions. Which I introduced last time, but I went pretty quickly and I glossed over a lot of things. So that means you've seen one before, but it's time to dig in a little bit deeper. So a binomial distribution is a discrete probability distribution Discrete means the values of the probability distribution take on specific numbers. It's not anything in a range. Probability means there's randomness involved, and distribution means that there's more than one possibility. You could have a distribution with only one possibility, but that'd be pretty boring. The outcomes, also known as values, are the number of successes out of the total number of trials or attempts. I'll say attempts. Where each attempt will either be a success or a failure. Examples. Flip 10 coins. What are the different possible number of heads and the probability of getting that many heads? So we have 10 attempts, but we're going to use the word trials. And we're going to give that a letter. We're going to say N. N is the number of trials. And then we're going to count the number of heads. This is the number of successes. We're going to call that either X or K, depending on which textbook or which app you're using. Each coin flip is either going to be a heads or a tails. So we want to know the probability of a heads on any single coin flip, which, if we imagine these are truly fair coins, is 0.5. We give that the letter P for probability. N is the number of trials. X or K is the number of successes. P is the probability of a single success. And of course, you could have a single failure. So 1 minus p is a probability of a single failure, which in this case is what? 0.5. So these are the 4 key numerical values that we care about with binomial distributions. And they're all you need to know in order to fully understand your probabilities, your expected values, etc. In fact, 1 minus p, since it comes directly from p, they're really just 3, but it helps to think about the failure as well. Success isn't always good. Failure isn't always bad. So we use the word success just to mean the outcome we are looking for. Doesn't have to be a good thing. Mammograms, in this context, success would be breast cancer, because that's what you're looking for when you conduct a mammogram. So success is definitely a bad thing, right? So don't think of success as being good or bad. It's just what's the event you're looking for, or what's the outcome you're looking for. And failure is the outcome that you're not looking for. In your health data set, success is a 1, which represents diabetes. That's not a good thing. In the employee data set, there is a binary variable in there, which is gender, which may not be accurate, but that's how the data is coded. And I think 1 is, I don't remember if 1 is male or 1 is female. There's no good or bad. It's just we've coded it. And if we create a binomial distribution, we just say 1 is success, which is female, because that's what we're looking for example. Anybody have questions about that? So one skill that I want you to be able to have is if someone gives you a verbal representation of a binomial distribution, I want you to be able to pull out the key numeric information, the number of trials, the number of successes, the probability of a single success, and the probability of a single failure. Okay, let's continue with that example. In 10 coin flips, how many heads do you expect? Assuming you don't have anything other than knowing that it's a 50-50 chance and you're flipping 10 coins. Talk with your neighbor. It's 5. Why? Because it's 50% of 10, right? So this is the expected value. Remember, we talked about expected value for any discrete probability distribution. In fact, for any distribution anywhere, it has an expected value. And the reason is 5 is 50% of 10, right? You could write 5 equals 0.5 times 10. How about if you had 30 flips? How many heads do you expect? 15, because 15 is 0.5 times 30. So for a binomial distribution, we don't have to go through that long x times probability of x and add them all up. for a binomial distribution, the expected value is just the probability of a single success times the number of trials. P times N. Often you see the N written first, NP. That's the same number. There is a standard deviation as well, but the standard deviation isn't really necessary for us to analyze these because we have a really nice, simple way to graph what's going on and look at it visually. So like I mentioned the other time, there's standard deviation for discrete probability distributions, but they're usually not super helpful. They're much more helpful with continuous probability distributions. So yeah, that's pretty important. So back to our 10 flips. Would you be surprised if 6 were heads? Talk about it with your neighbor. Would that give you pause? Would that make you say, huh, something's going on here? Gabby, you want to share your thoughts? I overheard you, so I'll put you on the spot. Yeah, so not surprised because in statistics, you don't expect to be exactly correct. And in this case, exactly correct would be landing exactly on the expected value. Okay. Okay, how about in 30 flips, would you be surprised to get 18 heads? Talk about that with your neighbor. Joel?
Further out from the 6 and went away, if it's still with the number.
All right, it's still pretty close. All right, I mean, that might be like Dorothy seeing one Technicolor flower. Yeah, maybe I didn't expect it, but that could happen in Kansas, right? I should add in here, you don't expect to be exactly correct, and 6 is very close to 5. I'm going to put the very close in quotations, though. Still pretty close to 15. Okay. How about let's jump all the way up to 100. On 100 flips, would you be surprised to see 60 heads? And how about one more question? In 1,000 flips, would you be surprised to see 600 heads? All right, talk about those 2 questions with your neighbor. Before I ask you to answer this, I'm going to ask you another question. Do you think that all of these are going to give you the same, or that I'm going to expect the same answer for each one of these questions? Do you think I expect you to say not surprised? Do you think the correct answer is not surprised for each of these questions? Okay. Now, don't think about the math. Don't think about the statistics. Think about what you know about me and people in general and teachers in general. How likely do you think it is that I would give you 4 questions that all have the exact same answer? Is that teachable? At a certain point, you're like, you don't have to keep asking me the same thing if you're expecting the same answer. So if you were talking to your neighbor and you're like, I bet it's different, because why would he keep asking me the same thing over and over again? You're doing statistics. You're saying it's very unlikely that Peter would ask me 4 questions that have no additional educational value. Therefore, I think it's more likely that he's asking me a question where the answer is going to be surprising. But let's go through this a little bit mathematically. I'll make a table. 10 flips, 6 heads, 6 out of 10 is our probability, our proportion. So this is n, this is x, and this is the proportion. Sorry, focus. Focus more. Focus, please. Thank you. Okay. Then we did 30 flips, 18 heads. 18 divided by 30 is what? It's the same as 6 over 10. Okay. Yeah, 60%. We said this is not surprising. 30, 18 out of 30, not surprising. We jumped up to 100 and 100 flips and 60 heads. 60 out of 100, also 6 over 10. And then even at 1,000 with 600 heads, 600 over 1,000, that is still 6 out of 10. So 6 out of 10 flips, 6 heads out of 10 flips, we said it was very close to the expected value. But the key is we need to define, what does very close mean in statistics? What does distance mean in statistics? All right, the not surprising, 18 compared to 15, that was still pretty close. But we need to decide if 60 is close, 60 out of 100 is close to 50 out of 100. And so what we're going to do next is the most important idea, not the most, a very important idea moving forward in statistics is, what does close mean? What does very close mean? Or what does distance, how do we measure distance? In statistics. Okay, so how far is it from here to Portland? Okay, is it, so 46 miles, and then Joel asked in minutes or in miles. You can measure distance in both of those ways, right? It takes an hour to get to Portland, or Portland's 45 miles away. There are lots of ways to measure distance. In statistics, we measure distance by probability, specifically, how likely is it to observe the data that we have. Flip 10 coins, get 6 heads. It's very likely to observe 6 out of 10 heads, or 6 heads out of 10 coins. It's still pretty likely to observe 18 out of 30 that are heads. But 60 out of 100, that's actually not very likely. And we're going to actually look at the visuals, but I want to emphasize, because this is one of the challenges moving forward, when we decide if something is surprising, when we decide something's far away in statistics, we are always asking about, how likely is it to observe what I actually saw? And if it's not very likely, then the distance is very far. Why did Dorothy decide she was far away from Kansas? Because it was unlikely that she would see the flowers. Right? As far as she knew, she was just lying on her bed. She was unconscious the whole time it was in the tornado. She didn't know that she moved physically anywhere, but when she woke up and said, it's not likely that I'm going to see these flowers, she decided she had been moved far away from Kansas. So to help us with this, we're going to use the app. Let's see. I got it fixed. It was just a broken link, so no longer broken. So here in week 4, we can use this app for visualizing binomial probability distributions. It's a nice, simple app. It uses X instead of K. So if I have 10 coins, or I'm flipping 10 coins, then N is 10. And the probability of getting a single heads is 0.5. And as soon as I put that in, it draws me the probability for each possible outcome. It could be 0 heads, 1 head, 2 heads, etc. And simply by hovering over, it'll show me the probability for getting exactly that value. So about a 0.25 chance of getting exactly 5 heads. And notice it's symmetric and 5 is in the middle. That's a very good sign that it's the expected value. There's still a 20% chance of getting 6 heads. So that's pretty high. And another thing we say is if we're surprised, it's not just the observation, it's the observation plus everything more extreme. So I'm going to go back to the notes. We measure probability, at least for deciding if something is surprising. By looking at our data or something more extreme. Because in a world where we get 6 out of 10, well, we could have gotten 7 out of 10, or 8 out of 10, or 9 out of 10, or 10 out of 10. When we come back to that, especially with our continuous probability distributions, when we look at data very visually. So 6 out of 10 is 20%, or it could have been 7, or 8, or 9, or even 10 out of 10. There is a number in there. It's just too small to see, I think. And so we can actually calculate that number. Probability of getting exactly 6 out of 10 heads, there it is, the 0.20. Or we could say, how about 6 or more? So there's a 38% chance of getting 6 or more heads. So that is not very surprising that we got 6 heads, right? All right, let's change. Let's do 30. There's our distribution, right? So the center of it is 15, which is still our expected value. And as you can see, getting, gosh, 23 or more would be really unlikely out of 30 coin flips. Because the larger your sample size, the more stable your estimates should be. So with 30 coin flips, that's a pretty good sample size. We would be surprised to get that far away from the expected value. 18, there's a only an 8% chance of getting exactly 18, but 18 or more, there's like an 18% chance. That's still pretty common. Does anybody remember our probability cutoff when we say something is surprising? 2 standard deviations gets us to that probability cutoff a lot of the times, but that's not a probability, it's a step size, but that's good. How about the probability? 5%. Let's add that in. Surprising in probability terms is 5% or less. So something is far away if the probability of observing it or something more extreme is less than 5%. That's a mouthful. I'm going to write it down. Let's see. Data is far away from what you expect if the probability of observing that data or something more extreme is less than 5%. That is ultimately how we measure distance in statistics, through a probability, not through what we normally think of as distance. Right? If you're really close to your parents, that probably means you talk to them often. It has nothing to do necessarily with whether they live 5 minutes away or 500 miles away. Right? If you're distant from a family relative, maybe that just means you don't see them much. There's so many different ways of measuring distance, and so you got to lock in that in statistics, we always mean probability. Let's go to 100. There's a 60. That's very far away from our expected value in probability terms, because to observe 60 or more, there's only a 0.028, a 2.8% chance. So here, I'll leave that up one more time, and I'm going to add it into my table here. This is surprising because it is far away, because the probability of observing 60 heads out of 100 flips or more is only 2.8%. In fact, let's add in our probabilities. Probability of X or more. This was 0.37. This was 0.18. Here we are at 0.028. How about 600 out of 1,000? Do you think that's going to be surprising or not surprising? Very surprising. Because the more data you collect, the more you expect to be close to your expected value. So the more surprised you are when you're far away. Basically a 0% chance. Basically, with a fair coin, it's never going to happen. You flip 1,000 coins, don't ever expect to get 600 heads or more. Right? I mean, by the time we get out to 544 heads, it's basically impossible. No way we're going to get up to 600. It doesn't even bother drawing where the 600 is. That also, by the way, is a really nice bell curve. Binomial distributions look like bell curves as you increase the number of trials. So unbelievable, maybe. Statistically impossible. Muy, muy lejos. All right, super far away. That'd be like you're as likely to see that as you are to take a baseball and throw it and have someone in Portland catch it. Right? It's like maybe it could happen, but don't bet on it. Approximately 0. Is it guaranteed to never happen? It's not guaranteed that it won't ever happen, because as Lloyd would say, you're telling me there's a chance. There's always a chance in statistics, but it's statistically impossible, which means don't ever expect it to happen. All right. Now, everything we've done so far has been with a 50-50 chance. And it's easy to think that binomial means 50-50 because it happens or it doesn't. But binomial doesn't mean the chance of a single success is 50-50. So let's do an example where the probability is more than 50-50. Research has shown that, let me just for fun here, data class data. 1, 2, 3, 4, 5, 6, 7. All right, so here's our class data collection spreadsheet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, that P equals 28 out of 38, or let's go ahead and just get a decimal for that. 74% of Chemeketa students have a pet. Couple of questions for you. First of all, is this a simple random sample? Is this a good simple random sample? It is not, because it was a convenience sample. It's just this class, right? So probably not the best data to use for statistics, but it's what we got, so we're going to use it. So choose a random student. What is the probability that they have a pet? Answer? 74%, or 0.74. Right? That's what probability means. It's our best guess based on the data that we've collected. Now, that's not 50-50, but someone either has a pet or they don't. Right? So it is binary, yes or no, but that doesn't mean the probability is 50-50. Okay, 10 students. How many do you expect to have pets?
About
7 out of 10 or 8 out of 10, right? 7 or 8, that's probably a good answer, right? 7.4 to be specific, but there's no such thing as 0.4 of a student. All right, so, this is a social science. We have to make this understandable to humans. 7 or 8 students, because I take my 0.74 times 10, I take my probability times my number of trials. And that's approximately 7 or 8. Yeah, okay. 40 students. How many do you expect to have pets? Let's answer this one visually. I practice using the binomial visualizer. What's n? 40. What's p? 0.74. We got to enter it as a decimal. Where's the center? Yeah, 29 or 30. In fact, it's going to be almost exactly 30, because 7.4 times 4 is 29 point something, right? Close to 30. Now, maybe you had done that arithmetic in your head, but if you hadn't, that was a pretty quick way to do it because visuals are a nice, fast way of understanding statistics. Okay. Let's ask a couple examples. Out of 40 students, what is the probability that exactly, how about 26 have pets? There's a nice formula for this. It's a super interesting mathematical formula. And if you take Stat 244 with me at some point, we'll dive into it. But we've got some useful technologies, so let's leverage it. What I put in for X, 26. And I'm doing exactly equal, there it is, 5.96 or 0.596 or about 0.06. All right, if you collected 40 students, there'd be about a 6% chance that exactly 26 have pets. Okay. How about what's the probability? This is how we often write it, that X equals 32 given N is 40 and P is 0.74. Let's not do equal, let's do greater than or equal. Because I don't want to just keep teaching you the same thing over and over again. It's very simple to do that using this app. We change our number to 32, and we change our shading to greater than or equal. There it is, about 25%. I'm pretty liberal with my rounding because it's probabilities. I don't expect it to be exactly 25.195% of the time, right? It's going to be roughly a quarter of the time. Your online homework might be picky about how many decimals you have to use. So we got to live with that. And if it frustrates you to no end and you bring it to me and it frustrates me, then I'm just going to withdraw the question. But each time I teach this class, I find the ones that drive me crazy and I pull them out. But in the real world, the difference between 25% and 25.195% in probability is meaningless. Yeah. Okay, would you be surprised if 32 out of 40 students had pets? No, because there's a 25% chance of at least that many. That's not surprising from statistics because it's more than a 5% chance. Now, this probability, 32 out of 40, which is our X over N, we call this the observed proportion. And statisticians in their wisdom decided to give this yet another symbol. Instead of calling it P, because that's the theoretical probability of a single success, they put a little caret over it. And it's called P hat. You're going to see P hat written in textbooks. You're never going to, or you're going to see P with the caret written in textbooks. You're never going to see me write that. You're going to see me write either the word observed proportion or sample proportion, or you're going to see me at least write P hat with the letters, because that's how I would write it using R, because there's no caret over a letter in R. Sample proportion. All right, so what is P hat if n equals 40 and x equals, where'd my app go? 23. I don't need a decimal, by the way. A fraction's totally fine because it's still a number. Yeah. And if you wrote it as a fraction, it's literally just 23 over 40. I'm going to stick with decimals, not percent. So I'm going to do 0.5, no, 57. Yeah, 0.575. Is this observed proportion surprising? Well, how do we answer that question? Yeah, and this is one place where probabilities get confusing because 0.575 is a probability, but that's not the one we used. That's not what we compare to the 5%. Right? This is technically not a probability, it's an observed proportion. What I want to know is, observing this data, would that be surprising? So I'm going to come back here. I'm going to rewrite this on another page because I'm going to need a little bit more space to talk about things. Let's see. Is 23 out of 40 students with pets surprising? And we need to compare or distinguish, tell the difference between p, p hat, and the probability of observing 23 or less. These are three different decimals that mean three different things. And it's one of the challenges of working with the binomial distribution is you have decimals floating around everywhere. P came from our data. This is the theoretical probability. What was the theoretical probability? Yep, exactly. And what is the number that we expect? What is the proportion that we expect? It wasn't 30, that's the number. What's the proportion? Yeah, in this case, it's 0.74, right? Because that's what our research told us, that 0.74 is a probability that any given student has a pet. Probability of a single success. Is it a success to have a pet? Is it better to have a pet? No, it's just the thing we're looking for. P hat is also a decimal. What's the decimal value of p hat here? 0.575. This is the observed proportion of our sample. But in order to decide if it's surprising, we need to look at the probability of seeing 23 or more extreme. And for that, we go to our binomial app. And we come up here and we have 40 students with a theoretical probability of 0.74. And now I see only 23. So I look at 23 or fewer. What's that decimal? Yeah, close to 0, but it's far enough away. It's still in the percentage terms. 0.017, right, which is 1.7%. And that's the decimal. That's the probability that we compare to our 5% cutoff. Not the 0.575 and not the 0.74, but the probability we get from using this app. Focus. Good. So again, is it surprising? Talk to your neighbor and come up with a nice, complete sentence or two that a non-statistician human would understand for why it would or would not be surprising to see 23 out of 40 students with pets. All right, I'm going to give it my shot this time because I heard lots of good conversation, lots of good sentences, which I think all were generally correct. I am surprised to see only 23 out of 40 students with a pet because the probability of 23 or fewer students is very small, i.e. less than a 5% chance. That's how I would write that in a sentence that a non-statistician human would probably understand. Does that mean it could never happen? Nope, because Lloyd would say you're telling me there's a chance, right? Even if there's only a 1 out of a million chance, there's still a chance of seeing 23 or fewer students out of 40. But it's very unlikely. And as a statistician, we say, good enough for me. That's surprising. There's something interesting going on here. Maybe it's students who are, studying and going to, they're all planning to be flight attendants. And like, I just can't, it's hard to keep track of a pet if I'm traveling all the time. And there might be something interesting about those 40 students that makes it worth asking more questions, which is one of the main reasons we do statistics, is to say, this is interesting. It's time to ask some more questions. All right. You all are ready to tackle the first half of Lab 2.